friends, today we will talk about a nonlinear data structure tree. A tree is also known as hierarchical relationship or a parent-child relationship. You all must have come across the term tree in real life. Just like a real tree, the tree in computer science has the notion of root, branches, leaves and nodes. Even the structure of this data structure is same as that of real tree except a little change. In computer science, we draw an inverted tree, that is the root of the tree is at the top and the leaves are at the bottom. Look at the diagram which depicts the tree data structure showing the root of the tree at the top. As tree also represent the parent-child relationship, so we use the term family tree like parent, child, ancestor, successor, grandparent, sibling, etc. while describing this data structure. Before proceeding the detail of this data structure, let us discuss the terminology associated with tree. A tree is a finite set of nodes which are connected by lines. Look at this diagram. This tree is composed of 7 nodes A, B, C, D, E, F and G. Here, the node A is the root of the tree at which tree starts. A line connecting two nodes of the tree is known as an edge. Edge is also known as branch. Here in this figure, the line connecting the node A and node C is a branch. Similarly, line connecting the node E and G is a branch. In this tree, there are 6 branches. All the nodes except root node has a parent node associated with it. Here in this diagram, A is the parent of B and C. Similarly, B is the parent of D and E. C is the parent of F. Node A does not has any parent because it is a root node. A node in the tree can have 0 or more children called its successors or descendants. Here B and C are successors of A. Similarly, D and E are successors of B. Nodes B, C, D, E, F and G are successors of A. Node A is called ancestor of B. Even we can say A is ancestor of D and E. Sometimes we also use the term grandparent. Here A is the grandparent of node D and E. Nodes having same parent are called siblings. Sometimes we use the term brothers or sisters. Here B and C are siblings as these have same parent A. Similarly, D and E are siblings as these have same parent B. E and F are not siblings because their parent is not same. A node having no child is called a leaf node or terminal node. Terminal nodes are referred as external nodes. Here, D, G and F are leaf nodes because these nodes do not have any child. A node having at least one child is known as non-leaf node or non-terminal node. A non-leaf node is also termed as internal node. Here, A, B, C and E are non-leaf nodes. Let us summarize these terms taking another tree. In this tree, there are total 8 nodes and 7 branches. A is the root node. Nodes B, C, D, E, F, G and H are successors of A. A is parent or predecessor of B and C. Even A is predecessor of D, E, F, G and H. Nodes F, G and H are leaf nodes, whereas nodes A, B, C, D and E are non-leaf nodes. Now let us define some more terms related to tree data structure. The first is path. Path between any two nodes in a tree is sequence of distinct nodes in which successive nodes are connected by edges. There must be exactly one path between the root and any other node in the tree. If there is more than one path between any two nodes, then that is not a tree but is termed as graph. The length of path is total number of edges which come across that path. Look at this figure. A path from root node A to node G is A to B, B to E, and E to G, which is of length 3 as there are 3 edges in this path. Similarly, a path from root node A to node F is A to C and C to F, which is of length 2 as there are 2 edges in this path. The height of any node in a tree is the length of the longest path from that node to any of the terminal node. The height of the root is treated as the height of the tree. In this tree, the node B is at a height of 2 because length of longest path from node B to leaf node is 2. Here the longest path from node B to leaf node is B to E, E to G. Similarly, node C is at height 1. The height of tree is 3, which is same as the height of root node A. The height of all the leaf nodes is 0. The degree. The degree of a node is defined as number of child nodes it has. A leaf node always has degree 0. Weight. The weight of tree is the number of external nodes available in that tree. As the external nodes are also known as leaf nodes, so the weight of tree is also known as number of leaf nodes in that tree. Look at the figure. In this tree, the node A has degree 2 as it has 2 child nodes. The node C has degree 1 as it has 1 child node. The weight of the tree is 3 as here are 3 leaf nodes in the tree. Then the term level. In a tree, each node is assigned a level number, which is length of the path from root node to that node. The level is also known as depth of the node. Root of the tree is at level 0. The immediate children of the root are at level 1. Look at this diagram. In this tree, the node A is at level 0. Nodes B and C are at level 1. Nodes D, E, and F are at level 2. The node G is at level 3. Okay, till now we have discussed the terminology of the tree. Here it must be mentioned for what a tree is used for. A tree is used to represent the hierarchical structures. Here is a tree showing the hierarchy of employees of a software company. In this figure, the root of the tree is the president of the company, under which vice presidents work. Under the vice presidents, there are project managers. These project managers control the project leaders, and many software engineers work under a project leader. Here is another tree showing the hierarchy of directory structure of Unix operating system. At the root of the tree is the root directory indicated by backslash. The root directory has subdirectories bin, devices, etc., home, lib, mnt, root, sbin, temp, and user. Under the bin subdirectory, there are files cp, ls, pwd, etc. Within the user subdirectory, there is a subdirectory bin. Now, let us discuss about a special kind of tree known as binary tree. A binary tree can be defined as finite collection of nodes where each node can have 0, 1, or 2 children. The nodes in the tree must be ordered. This means that nodes can be a left node or a right node. The left node means the node must be drawn on the left side of its parent, and the right node means the node must be drawn on the right side of its parent node. So, in the figure shown here, the node A is root of the binary tree, which is at the top of the tree. The left subtree of the root A is having nodes B1, C1, C2, D1, D2 and D3. The right subtree of the root A has nodes B2, C3, D4 and D5. Node B1 is the root of left subtree of A and B2 is root of right subtree of A. There is no node which has more than 2 children. That's why the tree is a binary tree. There is a special kind of binary tree known as complete binary tree. A binary tree is called complete binary tree if it contains maximum number of nodes it can have. We can also say that binary tree is a complete binary tree if all its levels are full. Look at this diagram. At level k, there can be at most 2 raised to power k nodes. The level 0 has 2 raised to power 0, that is 1 node. Level 1 has 2 raised to power 1, that is 2 nodes. Level 2 has 2 raised to power 2, that is 4 nodes. Level 3 has 2 raised to power 3, that is 8 nodes. Maximum number of nodes in a complete binary tree with height h is 2 raised to power h plus 1 minus 1. This displayed complete binary tree has height 3, so this tree contains 15 nodes as 2 raised to power 3 plus 1 minus 1 is 15. Number of leaf nodes in a complete binary tree with n nodes is n plus 1 by 2. Here in this binary tree, total number of leaf nodes are equal to 15 plus 1 by 2, that is 8 leaf nodes. Number of leaf nodes are equal to number of non-leaf nodes plus 1. Here the leaf nodes are 8 and non-leaf nodes are 7. The height of a complete binary tree is log of number of leaf nodes base 2. In the given tree, total number of leaf nodes are 8, so the height of this tree is 3. Okay, that's all about complete binary tree. There is another binary tree known as almost complete or nearly complete binary tree, in which all the levels are full except the last one. In the last level, nodes must be present as far left as possible. The binary tree shown in the figure is almost complete binary tree of height 3, in which all the levels are full except the last level. The last level has only 5 nodes which are as far left as possible. Here is another kind of binary tree, strictly binary tree. A binary tree is called strictly binary tree if all the non-leaf nodes of the tree contains exactly 2 children. That is, every non-leaf node of the binary tree contains left subtree and right subtree. In other words, we can say that each node in binary tree will have either no child or 2 children. There will not be any node that has only 1 child. The strictly binary tree shown in this figure has no node which is having only 1 child. Each node has either no child or 2 children. A strictly binary tree with n leaf nodes contain exactly 2n minus 1 nodes. In this strictly binary tree, there are 6 leaf nodes, therefore total number of nodes are equal to 11. Now let's come to the memory representation of binary tree. Now let us discuss the method with which a binary tree can be represented into computer memory. A binary tree can be represented into computer memory using 2 ways. One way is to represent it using array and another way is to represent it using linked list. The linked list representation of binary tree is the most commonly used and efficient one. Let us describe the linked list representation of binary tree first. Linked list representation of binary tree is the most common method to represent the binary tree into the memory. In this representation, each element of the tree is stored in a node having at least 3 parts. The figure shows the structure of node used to represent the binary tree into computer memory. The first part of the node is left part, which stores the address of left child node. The second part of the node is info part, which stores the element. The third part of the node is right part, which stores the address of right child node. The binary tree is made up of such type of nodes. The number of such nodes in a binary tree depends upon how many elements we want to store into the tree. The address of root node is stored in a pointer variable called root. If binary tree is empty, then variable root will have null value. Look at the diagram. It shows the linked list representation of binary tree containing 12 nodes. The root node of the tree contains the element A. The left subtree of A is rooted at B1 and the right subtree of A is rooted at B2. The left part of each node represents the address of left child and the right part of each node represents the address of right child. The cross sign in the left or right part of the node represents null value indicating no child node. Sequential representation of binary tree. Let us discuss another way to represent the binary tree. Binary tree can also be represented using array. This representation is also known as sequential representation. In this representation, root of the tree is always stored at the first array index and its left and right child is stored at second and third index respectively. In general, if a node of the binary tree occupies kth index of the array, then its left child will be stored at 2 into kth array index and its right child will be stored at 2 into k plus 1 array index. The sequential representation of a binary tree of height h will require an array size of 2 raised to power h plus 1 minus 1. In the shown binary tree, the size of the array is taken as 2 raised to power 3 plus 1 minus 1, that is 15, because the height of the tree is 3. Here, A being root of binary tree is stored at first array index, so its left child B1 occupies second array index and its right child B2 occupies third array index. As B2 is stored at third array index, its only right child C3 will occupy 2 into 3 plus 1, that is 7th array index. Similarly, the element D1 being left child of element C2 at index 5 occupies 2 into 5, that is 10th array index. It is to be noted that in the sequential representation of the binary tree, many array positions have null values. As in this figure, there are 7 vacant positions in this array. So, this array representation is efficient only when binary tree is complete binary tree in which all the levels of the tree are full, and hence there will not be any vacant position in the array. Similarly, the array representation can be used efficiently to some extent if the binary tree is nearly complete binary tree, in which all the levels of the tree are full except the last one. Hence, the maximum vacant positions in the array will be less than 50%. Traversing the binary tree. Let us discuss the most important operation that is applied to the binary tree, traversing. Traversing is the process of visiting each node in the tree. When a tree is traversed, its entire collection of nodes is visited. There are 3 standard methods for traversing of binary tree. All these traversal methods differ in the order of visiting root node, left child and right child. The 3 traversal techniques are shown in this figure. The traversals are pre-order traversal, in-order traversal, and post-order traversal. Let us discuss these traversal techniques one by one. Pre-order traversal. The pre-order traversal is also known as depth first order. In this traversal, firstly, root is visited, then recursively pre-order traversal on the left subtree is performed, and then pre-order traversal on the right subtree is performed. This traversal method is also known as root left right traversal. As mentioned, first root is visited, then left subtree is visited, and then right subtree is visited. Look at the figure. In this given binary tree, first of all, root of the tree is visited. After visiting root node, left subtree of this node is visiting in pre-order manner, postponing the traversal of right subtree. Here, first of all, root 10 is visited. Then the left subtree rooted at 5 is visited in pre-order manner, that is root left right manner. Here, root of left subtree 5 is visited, and then root of left subtree of 5, which is node 2, is visited. As the node 2 has no left child, so the right child of 2 is checked. As the right child of 2 is also not present, it means left subtree of node 5 has been traversed. Now is the turn of right child of node 5. As the right child of 5 is not present, it means the left subtree of root node 10 has been traversed, and now is the turn of right subtree of root node. In the right subtree, the root node 15 is visited first, and then the left subtree of 15 is traversed. This left subtree contains only one node 12, which is traversed. Now it is the turn of right subtree of node 15, as right subtree contains only one node, so this only node 18 is visited. At this point, the whole right subtree of node 10 has been visited, and hence we stop this procedure as all the nodes have been visited in root left right order. The traversal order comes out to be 10, 5, 2, 15, 12, and 18. In-order traversal. Now let us move to another traversal method, in-order traversal. The in-order traversal is also known as symmetric order. In this traversal, firstly, whole left subtree is traversed recursively in in-order manner, then root is traversed, and then right subtree is traversed recursively in in-order manner. This traversal method is also known as left root right traversal. Look at the figure. In this tree, firstly left subtree of 10 is visited in left root right order, after which the root of the tree 10 is visited, and then the right subtree of 10 is visited in left root right order. Here, the left subtree of root node contains the element 5 and 2. In this subtree, 5 is the root which will be traversed after its left subtree. In the left subtree of 5, there is only one element 2 which will be traversed. After traversing 2, the node 5 is traversed. Now it is the turn to move to the right subtree of node 5, which contains no element. At this stage, the left subtree of node 10 has been traversed, so it is the turn of node 10. After traversing 10, the right subtree, which contains the element 15, 12, and 18, will be traversed. In this right subtree, 15 is the root which will be traversed after its left subtree is traversed. As the left subtree of 15 has only one node, so this node 12 is traversed. After this, it is the turn of node 15. After traversing 15, the right subtree of 15 is visited. as the right subtree contains only one node. So this node 18 is traversed and the process stops as all the nodes of the tree are visited. The traversal order comes out to be 2, 5, 10, 12, 15 and 18. Post order traversal. Now let us discuss the last traversal method, post order traversal. In post order traversal, firstly, the left subtree is traversed in post order manner, then right subtree is traversed in post order manner, and then the root is traversed. This traversal is also known as left right root traversal. Look at the figure. In this tree, firstly, the left subtree of root node 10 is visited in left right root order, after which the right subtree of root node 10 is visited in left right root manner, and then the root node 10 is visited. Here, left subtree of root node contains the element 5 and 2. In this subtree, 5 is the root which will be traversed after its left subtree and right subtree are traversed. In the left subtree of 5, there is only one element 2 which will be traversed. After traversing it, the right subtree of 5 is traversed. But right subtree of 5 does not exist, so the node 5 is visited. Now it is the turn to move to the right subtree of node 10, which contains three elements 15, 12 and 18. In this subtree, 15 is the root which will be traversed after traversing its left subtree and right subtree. The left subtree of 15 contains only one element 12, which is traversed here. After this, it is the turn of right subtree of 15, which has one element. So this element 18 is traversed here. Now the element 15 is traversed, which is root of right subtree of 10. At this stage, only the root element of the tree is left. So this element is visited here and the traversal order comes out to be 2, 5, 12, 18, 15 and 10. So in all these traversal methods discussed so far, the left subtree is always traversed before the right subtree. The difference between traversal method lies in the order at which root of the tree is traversed. In pre-order traversal, root is traversed before its left subtree as well as right subtree. In order traversal, root is traversed between the traversals of its left subtree and right subtree. In post-order traversal, the root is traversed after the traversal of its left subtree as well as right subtree. In the nutshell, we have discussed the nonlinear data structure tree and its terminology. Then we have discussed a very special kind of tree, binary tree, and its types, a complete binary tree and almost complete binary tree. The memory representation of binary tree has been discussed, and at the end, we have discussed the traversal techniques of binary trees. In the part 2 of this topic, we will discuss the binary search tree and its operations. Thank you very much.